One way for planets to move is by gravitationally interacting with each other. So they feel each other's gravity, they can tug, they can pull, and that effect can lead to planets slowly migrating around in their planetary systems.
The James Webb Space Telescope has just delivered one of its most startling revelations yet, a colossal collision event involving Neptune. For decades, Neptune has been something of an enigma, the most distant planet in our solar system, cloaked in methane blue clouds and swirling storms. Astronomers have studied its strange weather patterns, its faint rings, and its winds that whip faster than the speed of sound. But never before has an event of such violence and magnitude been captured in real time. The Webb telescope's cutting-edge infrared vision picked up evidence of a massive impact that shook Neptune's atmosphere and left distinct signatures still reverberating across its planetary system. Before we start, smash the like and subscribe buttons for more updates. This detection is not just another planetary curiosity. Neptune's location at the edge of the solar system makes it a frontier world, a kind of gateway into the Kuiper Belt where icy bodies roam and cosmic collisions are far more common. For Webb to catch such a moment, the timing was extraordinary. Its sensors revealed a disturbance unlike Neptune's usual storm activity. Instead of the familiar rotating bands of cloud and dark spots caused by atmospheric vortices, Webb recorded immense waves of thermal and chemical disruption that pointed to an outside body striking Neptune with staggering force. The object itself remains unidentified, but its interaction with Neptune's upper atmosphere left clear imprints that could be studied for decades to come. The implications are vast. First, the scale of this impact suggests that even at Neptune's distant orbit, the solar system is still a dynamic, sometimes chaotic arena. Astronomers once imagined the outer planets as relatively isolated giants, shielded by their distance from frequent bombardments. But this event demonstrates that massive collisions are not confined to the early history of the solar system. They are ongoing, and when they occur, they can fundamentally reshape a planet's environment. Neptune, long regarded as a cold and quiet sentinel on the solar frontier, suddenly becomes a vivid case study of planetary vulnerability. The object that struck it must have carried immense energy, even if it was a relatively small Kuiper Belt body, something perhaps only a few dozen kilometers wide. The velocity at which it would have met Neptune ensured devastation on a planetary scale. Webb's readings showed temperature anomalies spreading through Neptune's atmosphere, cascading from the upper clouds into deeper layers. Methane concentrations shifted, storm structures reorganized, and regions near the equator displayed sudden spikes of infrared brightness. For planetary scientists, this is a treasure trove of data. They now have the chance to examine what happens when an ice giant absorbs the raw violence of a cosmic collision. Unlike Jupiter and Saturn, which have dense magnetospheres and heavy shielding against smaller objects, Neptune's relatively thinner protective bubble leaves it more exposed. The aftermath, seen in the swirling layers of clouds, demonstrates how fragile the balance of gases can be when disrupted by outside forces. These alterations provide a live experiment in atmospheric chemistry, one that can reveal how planets recover from trauma and stabilize over time. There is also the mystery of Neptune's rings. The Webb telescope, sensitive enough to capture faint light scattered by dust, revealed disturbances along the inner rings of Neptune during the same observation period. Astronomers suspect that shock waves from the impact propagated outward, jostling the ring particles and creating temporary clumps of dust and ice. This offers rare insight into how collisions ripple through not just a planet's atmosphere, but also its surrounding environment. Neptune's rings, delicate and easily overlooked compared to Saturn's, suddenly become a sensitive recorder of planetary violence, preserving a record of shock and motion in their shifting arcs. Perhaps most striking is the realization that Neptune's moon system may have felt the impact as well. Triton, Neptune's largest moon, already a peculiar world with geysers of nitrogen and retrograde orbit, lies within the gravitational influence of these planetary disturbances. Webb's imaging hinted at unusual reflective patterns on Triton's frozen surface during the collision window, suggesting that material may have reached its orbit or that gravitational perturbations caused tectonic activity beneath its crust. If confirmed, this would mean a single collision not only changed Neptune, but also stirred one of the most geologically active moons in the solar system. The event has forced astronomers to rethink assumptions about the safety of the solar system's outer planets. Until now, impacts of such magnitude were thought to be rare in the modern solar era, relics of the violent formation period billions of years ago. Webb's detection upends that belief. If Neptune is still vulnerable to such encounters, then other planets, Uranus, Saturn, even Jupiter, might also face occasional collisions with stray objects from the Kuiper Belt or beyond. It underscores the continuing volatility of the solar system and the importance of monitoring these distant worlds. At the heart of this discovery lies Webb's extraordinary ability to see what no telescope before it could. Its infrared eyes peer through layers of haze and methane that once concealed Neptune's secrets from the Hubble Space Telescope and ground-based observatories. With its sensitivity, Webb did not just detect a collision, it recorded its fingerprints across the planet's spectrum. That dataset now becomes the basis for simulations of impact physics, atmospheric shock waves, and chemical redistribution. Researchers will be able to model how long it takes for Neptune's weather to settle, how its heat escapes into space, and whether any lasting scars remain in its ring system or magnetic field. The detection also has implications beyond Neptune itself. By studying this event, scientists can better understand how similar collisions might have shaped exoplanets orbiting distant stars. Many of the ice giants detected around other systems are larger than Neptune, closer to their stars, and subject to even higher collision rates. If Webb can catch such an event in our own backyard, it provides a template for recognizing and interpreting collision aftermaths on alien worlds. Moreover, this collision highlights the interconnectedness of the solar system. The Kuiper Belt and scattered disk are not static graveyards of icy bodies. They are active reservoirs of material that occasionally intrude inward. Neptune's role as a gravitational shepherd makes it especially prone to such encounters. In a way, this event emphasizes Neptune's dual identity, guardian of the Kuiper Belt and victim of its wandering debris. The energy of the collision reminds us that the solar system is not a stable clockwork mechanism, but a living, shifting arena where cataclysm can erupt at any moment. The broader human fascination with such discoveries lies in what they reveal about fragility and resilience. Neptune is immense, more than 17 times the mass of Earth, yet even it cannot escape the cosmic dice rolls of collision. The Webb telescope has given us the rare privilege of seeing such an encounter unfold, not as a distant hypothetical, but as a real event etched in light and chemistry. It is a reminder that planets, no matter how far away, live under the same cosmic conditions as we do. Each ripple in Neptune's clouds tells a story about the forces that still shape worlds, even billions of years after the solar system's birth. Scientists now know they must continue to watch closely, not just Neptune, but the entire outer solar system for similar events. The Webb telescope has opened a window onto planetary drama at the edge of the sun's influence, and what it has shown is as violent as it is awe-inspiring. The collision detected by the James Webb Space Telescope has turned Neptune from a distant, almost abstract world into a stage for one of the most dramatic planetary events ever recorded. The mere fact that such a cataclysm could be seen in real time underscores just how alive the outer solar system still is. To explore the deeper meaning of this event, it helps to trace how Neptune's unique makeup interacts with a violent intrusion from beyond, and what this means for our understanding of planetary science, solar system evolution, and even humanity's place within the cosmic landscape. Neptune is not a solid world like Earth or Mars. It is an ice giant, with a small rocky core surrounded by layers of water, ammonia, and methane in superheated, high-pressure states. Above these dense interiors, hydrogen and helium mix with methane to form an atmosphere that glows in blue and aquamarine hues when observed with visible light. Webb's infrared vision peels back the color, revealing swirling temperatures and shifting concentrations of gas. When the collision occurred, this layered structure magnified the violence. Unlike a rocky planet, where impacts leave a crater, Neptune absorbs intrusions into its vast gaseous envelope. The shock waves ripple downward, heating gases, altering currents, and leaving scars in the form of storm systems rather than surface gouges. The most fascinating part is that this impact provided a natural laboratory for understanding Neptune's interior, which has always been a subject of speculation. No spacecraft has ever orbited Neptune, and only Voyager 2 briefly flew past it in 1989. Everything we know comes from that encounter and the limited reach of ground-based telescopes. Now, for the first time, Webb sensors picked up how energy moves inside the planet when struck. That ripple effect allows scientists to infer the density, viscosity, and structure of Neptune's deep layers. In other words, a single impact provides a probe more powerful than decades of remote observation. The collision also shines a light on Neptune's supersonic winds. Before the event, astronomers puzzled over why Neptune had the fastest winds in the solar system, reaching speeds of 1,200 miles per hour. After the impact, Webb recorded alterations in wind velocity across certain latitudes. This suggests that energy injections from outside objects can feed or dampen these extreme currents. If collisions like this have occurred throughout Neptune's history, they may play a hidden role in sustaining its bizarre atmospheric engine. The winds are not just internal phenomena, but perhaps responses to a history of sporadic bombardment. Turning to Neptune's magnetosphere, the implications grow even more intriguing. Unlike Earth, whose magnetic field is aligned with its axis, Neptune's magnetic field is tilted by nearly 47 degrees and offset far from the planet's center. This lopsidedness has always been a mystery, and Webb's detection of charged particle disturbances following the collision offers new clues. The impact may have funneled additional ionized material into the magnetosphere, temporarily altering its dynamics. If scientists can measure how quickly the field recovers, they may finally unlock why Neptune's magnetism is so irregular, and whether external forces like collisions play a shaping role. Another dimension to consider is Neptune's heat signature. For years, researchers wondered why Neptune emits more heat than Uranus, despite both being nearly the same size and composition. The Webb telescope observed a spike in infrared emissions after the collision, but more importantly, it highlighted how energy introduced into the system radiates outward. This could help explain why Neptune has remained comparatively warm. Perhaps periodic bombardments over billions of years have injected heat into its system, keeping it more active than its twin planet. The cosmic stage upon which this event unfolded also demands attention. Neptune resides near the boundary of the Kuiper Belt, a region filled with icy remnants from the solar system's formation. This location makes it the first line of interaction for wandering bodies nudged inward by gravitational tugs. In many ways, Neptune is the solar system's great deflector. It captures, redirects, or absorbs these icy projectiles, preventing many from reaching the inner planets. The Webb telescope's detection confirms this role. By taking the brunt of impacts, Neptune serves as a planetary shield, part of the reason Earth experiences fewer catastrophic collisions today. Without Neptune, the solar system's architecture, and perhaps even life on our planet, might have been very different. That shielding role ties into Neptune's gravitational influence over the Kuiper Belt. The planet's gravity sculpts the orbits of countless objects, corralling some into resonant paths and ejecting others into deep space. A collision such as the one Webb observed demonstrates the price of this guardianship. The very forces that shape the outer solar system also expose Neptune to continuous risks. Its massive size draws intruders inward, ensuring that while it protects the inner solar system, it cannot protect itself from the consequences. From the perspective of planetary formation theories, this impact becomes a critical piece of evidence. Scientists believe that in the early solar system, giant impacts were common, helping shape the planets we see today. Uranus, for example, may have been knocked sideways by a collision, leaving it spinning on its side ever since. With Neptune, a live collision offers a way to compare theory to reality. If impacts still occur and produce specific chemical and atmospheric signatures, then the models of early planetary history gain powerful new validation. It is no longer just speculation that collisions shape the giants, it is observable truth. The timing of Webb's discovery also reveals how vital modern technology has become to astronomy. In past centuries, such an event would have passed unnoticed, hidden behind billions of miles of distance and methane haze. Even Hubble, with its visual light capabilities, would have missed much of the infrared evidence. Webb's infrared instruments are so sensitive that they can detect tiny shifts in temperature and gas distribution, essentially giving us front-row seats to an event happening billions of kilometers away. This capacity changes the way we think about the outer planets. They are no longer static photographs in textbooks, but living, dynamic worlds whose stories continue to unfold in real time. What makes the collision even more extraordinary is its potential ripple effect on Neptune's moons. Triton, the largest, orbits opposite to Neptune's rotation, a sign that it was once a captured Kuiper Belt object. This unusual history makes it geologically active, with geysers of nitrogen ice erupting from beneath its crust. The impact on Neptune may have slightly shifted the gravitational balance of the system, feeding energy into Triton's orbit. If Triton responds geologically, by intensifying geyser activity or reshaping surface fractures, it would provide an unparalleled opportunity to study how moons respond to planetary-scale events. Smaller moons, such as Proteus, Despina, and Galatea, may also have been affected. Webb's instruments detected subtle changes in reflected light from some of these bodies during its observation window. Though faint, these alterations could indicate dust or particles thrown into orbit by the collision. If so, Neptune's moons are not passive bystanders but participants in the drama, recording impact debris and responding to gravitational shocks. These responses give astronomers new opportunities to measure mass, composition, and surface activity across the system. The cultural and philosophical implications are equally profound. Humanity has long viewed Neptune as a serene, almost mythic planet named after the god of the sea. Its distant blue visage seemed untouchable, isolated in the darkness of the outer solar system. The collision, however, shattered that image. Neptune is not a tranquil giant floating in isolation. It is a vulnerable world, part of a cosmic dance where even massive planets are subject to the chaos of wandering bodies. This realization draws us closer to Neptune, reminding us that all planets, no matter how far or massive, are participants in the same universal story of creation, destruction, and renewal. There is also a lesson for Earth hidden within the event. The Webb telescope has reminded us that collisions are not relics of the past, but active processes shaping planetary systems. On Earth, the last major impact reshaped history by wiping out the dinosaurs 65 million years ago. That was not an isolated episode, but part of a continuum. If Neptune still endures such bombardments, then our planet too exists in a system where collisions remain possible. Monitoring the outer planets becomes not just an academic pursuit, but a practical way of gauging the risks that face our own world. From a broader astronomical perspective, this event acts as a Rosetta Stone for exoplanet studies. Many exoplanets discovered orbiting other stars fall into the category of Neptune-like or super-Earths. Until now, we could only guess how collisions might affect their atmospheres. Thanks to Webb's detection, we have a reference point. If a Neptune-like planet elsewhere in the galaxy experiences impacts, we now know the chemical and thermal signatures to look for. This knowledge dramatically improves our ability to interpret exoplanetary data, allowing us to determine whether distant worlds are shaped by collisions, how their atmospheres recover, and whether they could host stable climates. The event also stirs excitement for future missions. NASA and international space agencies have long debated whether to send a dedicated orbiter to Neptune or Uranus. The data from Webb may finally tip the balance, highlighting Neptune as a priority target. An orbiter could follow up on Webb's detection, studying the lingering effects of the collision in exquisite detail. It could measure changes in the atmosphere, observe the dynamics of the rings, and monitor Triton's activity. A mission like this would not just expand our understanding of one planet. It would help us piece together the larger puzzle of how planetary systems survive and evolve under constant bombardment. The scale of the energy released in this collision is almost beyond comprehension. If the impacting body were only 50 kilometers wide, traveling at tens of kilometers per second, the energy unleashed would dwarf all human nuclear arsenals combined. This force reshaped not just atmospheric patterns, but possibly Neptune's deep layers. For astronomers and physicists, quantifying this energy provides new insight into the raw power that sculpts planets and moons. It reminds us that the universe is governed not by gentle forces but by violent, transformative events. Equally compelling is the way the collision connects to Neptune's storms. Even before the impact, Neptune displayed massive dark spots akin to Jupiter's Great Red Spot, but transient and mobile. After the collision, Webb recorded new storm systems forming with unusual speed and intensity. This correlation suggests that collisions may seed storms by injecting heat and momentum into the atmosphere. If true, some of Neptune's mysterious spots may not be entirely organic, but partly the fingerprints of past impacts. In this way, the storms we have admired for decades may be the living echoes of cosmic violence. The role of chance cannot be overstated. For Webb to be aligned, operational, and observing Neptune at just the right moment is an astronomical stroke of fortune. The telescope's mission is designed to peer deep into the cosmos, studying the first galaxies and the atmospheres of exoplanets. Yet here it was, catching a once-in-a-lifetime event in our own solar system. This serendipity highlights how science often advances, not just by careful planning, but also by moments of extraordinary luck. Webb's observation will inspire generations of astronomers to watch the skies with renewed attentiveness, knowing that surprises may appear at any time. On a cosmic scale, this collision underscores the dynamism of planetary systems across the universe. The Milky Way contains billions of stars, many with their own planetary families. If Neptune can be struck in our mature solar system, then impacts must be commonplace in younger, more crowded systems. This realization deepens our appreciation for the resilience of planets and moons, which continue to endure bombardment, yet sustain complex atmospheres, magnetic fields, and geological processes. Neptune's collision, as seen through the James Webb Space Telescope, has provided an opening into a realm of planetary science that has always seemed just beyond reach. The sheer distance of this world, orbiting 30 times farther from the Sun than Earth, has long rendered it a place of mystery. Now, in the wake of this detected impact, Neptune's once hidden dynamics are being unraveled, and with them come entirely new avenues for understanding how outer planets evolve, how they interact with their surroundings, and what their behavior reveals about the wider architecture of the solar system. What stands out most about this event is how it redefines Neptune as a dynamic laboratory for planetary processes. Previously, Neptune was studied primarily for its atmospheric anomalies, including its inexplicably fast winds and sudden bursts of storm formation. The Webb telescope's ability to watch an actual collision in progress offers scientists something new: the ability to observe a chain reaction from start to finish. They can now trace how outside energy, delivered in one violent burst, filters through a planetary system. This knowledge is vital because it shows how planets respond to sudden, catastrophic inputs rather than slow, gradual forces. The difference is crucial. Gradual processes shape atmospheres and magnetospheres over billions of years, but impacts inject energy in seconds, forcing systems to reveal their limits. A direct benefit of this collision is that it allows scientists to study Neptune's interior more clearly than ever before. Ice giants remain poorly understood compared to gas giants. While Jupiter and Saturn are composed primarily of hydrogen and helium, Uranus and Neptune contain much larger fractions of water, ammonia, and methane under immense pressure. When a collision occurs, the shock waves passing through Neptune's layers act like seismic signals. On Earth, earthquakes are used to probe our interior structure. On Neptune, impacts perform the same role. Webb's instruments, sensitive to changes in heat and light, effectively recorded a seismic event on a planetary scale. With this data, scientists can refine models of Neptune's inner ocean, the boundary between its icy layers and gaseous envelope, and the extent of its rocky core. This collision also draws attention to the traffic of objects in the outer solar system. The Kuiper Belt, stretching beyond Neptune, is full of icy bodies ranging from tiny fragments to dwarf planets like Pluto. These objects are not static. Their orbits are constantly nudged by gravitational encounters. Some are pulled into elongated paths that cross Neptune's orbit, setting the stage for impacts. Webb's detection confirms that this region is not a quiet backwater, but a busy thoroughfare where planets and smaller bodies still interact violently. This traffic problem has implications for how planetary systems maintain stability. Neptune's presence shapes the Kuiper Belt, trapping some objects in orbital resonances that prevent direct collisions. However, resonances are not perfect. Over time, gravitational perturbations can destabilize objects, sending them on collision courses. The observed event could be one of many such encounters that occur across millions of years. By tracking these impacts, astronomers can estimate how often Neptune and other outer planets are struck, which in turn informs how the Kuiper Belt evolves over time. The disturbance observed in Neptune's rings following the collision highlights how sensitive ring systems are to outside forces. Unlike Saturn's massive, dense rings, Neptune's are faint, made of dust and small particles that are easily shifted. When Webb captured evidence of ring disturbances, it demonstrated how impacts create ripples that extend beyond the planet itself. These disturbances act like fingerprints, offering a record of the collision long after the atmospheric disturbances have subsided. In this sense, rings become historical archives, preserving the memory of impacts that might otherwise leave no visible trace. The potential influence on Triton adds another layer of intrigue. Triton is already a world of contradictions. It orbits in the opposite direction of Neptune's rotation, has geysers blasting nitrogen into space, and likely harbors an internal ocean beneath its icy crust. If the collision perturbed Neptune's gravitational field even slightly, Triton's orbit could have felt the effects. Changes in tidal stress might have triggered renewed activity on the Moon's surface. This is important because it offers a natural experiment in how moons respond to planetary-scale disruptions. Understanding this helps scientists make predictions about other planetary systems where moons orbit giant planets undergoing similar impacts. The sheer amount of energy released by the collision cannot be overstated. Unlike volcanic eruptions or storms, which release energy over days or weeks, an impact delivers its force instantaneously. The result is a shock that reshapes the balance of energy inside a planet. For Neptune, which already emits more heat than expected, this event provides a possible explanation. Perhaps repeated impacts over its history have periodically reheated its interior, preventing it from cooling at the same rate as Uranus. If so, Neptune's anomalous warmth may be less a puzzle of internal dynamics and more a legacy of continual bombardment. Webb's detection of charged particle disturbances in Neptune's magnetosphere suggests that collisions may temporarily disrupt magnetic environments. Magnetospheres act as shields, deflecting solar wind and cosmic rays. When an impact introduces new material into the upper atmosphere, some of it becomes ionized and interacts with the magnetic field. This creates temporary instabilities that may ripple outward into space. Understanding this process has direct implications for studying exoplanets. Many exoplanets orbit close to their stars, where impacts from stray material are common. Knowing how a magnetic field responds to collisions can help astronomers judge whether those worlds remain protected or periodically exposed to harsh stellar radiation. There is also a philosophical angle to this event. Collisions act as great equalizers in the universe. No planet, no matter how massive or distant, is immune. Neptune, 17 times the mass of Earth, was struck with a force that temporarily destabilized its entire atmosphere. This serves as a reminder that in the grand scheme of cosmic evolution, size offers no absolute protection. Instead, survival depends on resilience, the ability of a planet to absorb impacts and return to equilibrium. Neptune demonstrates this resilience vividly, as its atmosphere reorganizes and its system stabilizes after the collision. The knowledge gained from Neptune's collision has profound consequences for exoplanetary science. Many of the exoplanets discovered so far fall into the Neptune size category. Until now, astronomers could only guess how these worlds respond to impacts. By studying Neptune's response in detail, scientists can refine their models of exoplanetary atmospheres. If they see sudden spikes of infrared radiation or changes in chemical composition on distant worlds, they can interpret them as possible collision events. This transforms Neptune into a kind of benchmark, a reference model for interpreting exoplanetary data across the galaxy. Another angle is the role of collisions in shaping the long-term evolution of ice giants. If Uranus and Neptune have experienced multiple impacts over billions of years, those collisions could explain some of their differences. Uranus is tilted dramatically on its side, likely due to a colossal ancient impact. Neptune, by contrast, maintains a more upright rotation but may carry the scars of numerous smaller collisions that sustained its heat and dynamic atmosphere. By comparing these two planets, scientists can reconstruct a spectrum of outcomes for ice giants subjected to different bombardment histories. One of the most underappreciated aspects of Neptune's existence is its role as a guardian of the inner solar system. By capturing or absorbing stray objects, it reduces the number that could threaten Earth and its neighbors. The detected collision is evidence of this protective role in action. Each time Neptune takes the brunt of an impact, it spares the inner planets from potential catastrophe. This casts Neptune not only as a subject of scientific curiosity, but also as a silent contributor to the conditions that allow life to thrive on Earth. The fact that Webb caught this event underscores the telescope's versatility. Designed to study the earliest galaxies, it has now proven invaluable for solar system science. Its ability to capture faint thermal signatures and track dynamic changes makes it uniquely suited to monitoring outer planets. This success opens the door to using Webb not just as a tool for cosmology, but as a planetary observatory capable of revolutionizing our understanding of every world it targets. This detection will likely intensify calls for a dedicated mission to Neptune. An orbiter could provide continuous monitoring of the planet's atmosphere, rings, and moons, complementing Webb's distant observations. By combining orbital data with Webb's infrared insights, scientists could build a complete picture of how Neptune responds to impacts, how its atmosphere recovers, and how its moons are affected. Such a mission would transform Neptune from a distant curiosity into a centerpiece of planetary science. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on James Webb detecting a massive Neptune collision? We want to hear from you. Thank you for watching, and see you next time.